Hey, good morning. All right, got a new unit today. We are going to be working largely with the periodic table in this unit. So we got new notes, new units, new notes, new page, unit 5. And again, this one is all about the periodic table. And we're going to start 5.1 with Lewis dot diagrams and groups and families. This is going to end up being on the periodic table here, and this is kind of something we do with the periodic table. So starting off, valence electrons. And I will most often call them VE from now on. So valence electrons, VE. And these are electrons that are on an atom's outermost energy level. And they're only the electrons at outermost energy level. For hydrogen, it's pretty easy. Hydrogen just has one electron. So there's our 1s1 electron, 1 valence electron. That's it. Helium, very similar. There's only one level on helium. And so both those electrons are on the outer shell, the outer level. And so both of them are valence electrons. Gets a little bit more difficult. We start moving past. So next up, we would have lithium, whose 1s is filled up. So there's the 1s electrons, and then you move to the second energy level. And he has one electron on the 2s. And this here is now the valence shell. Those first two electrons don't count. So we're back to just one valence electron. So lithium has only one valence electron. Beryllium, very similar, has two electrons on the first energy level and then another two on the second energy level. Again, those first two don't count. They're not valence. They're on a lower energy level. So it's only these two right here that are your valence electrons. I'm going to skip ahead a little bit here to oxygen. And oxygen, just like those first two, has two electrons on the first energy level. First two electrons, when you're drawing these dot diagrams, first two electrons go together. Why is that the case? Well, because they're paired up. Probably better to write it with our arrow diagrams. The s orbital, up arrow, down arrow. So those first two electrons go together. After that, so if we're to finish our electron configuration, we would say oxygen is 2p4. So we've got 4 more electrons to add. But these next 4, watch how I add them. Got one here. Then I go to another corner and finally the third corner. So again, counting these up, 1, 2, 3, 4, 5. 3, 4, and 5 are spaced out. So the first two electrons go together. The next three get spaced out, and that's due to Hund's rule. And finally, again, we've got a fourth electron. We've got a total of 6 valence electrons. Right now, I've only drawn 5. So finally, we come back and pair up number 6. Again, that's the bus seat rule. Go open, 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 and then back tier number 6. All right, so there's oxygen and his valence electrons, and he has a total of 6 valence electrons. And again, you can see that 2 there, 4 more there. They're both on the second energy level. 2 in the S, 4 more in the P, but they're all on the second energy level. All right, so next up, I'm going to skip down a little bit, draw a slightly bigger atom. I'm going to skip to scandium. All right, like pretty much everybody else, that first energy level gets closed off for scandium pretty quick. Moves to the second. So this helps 1s2, 2s2, then we go 2p. So 2p is filled up, and we move to the third energy level. Again, we always start with that S. So there's our 3s2. And we go 3p, again, open, open, open. Fill the seat, fill the seat, fill the seat. So 3p is filled up, and next up, we go to the fourth energy level. So we say 4s2, and now we have to stop and think, what happens after 4s2? We go to 3d, and we're going to stop right there. That's where scandium is. He's 3d1. So 3d1, just 1 electron. But the important part is we went back to the third energy level. We have the fourth energy level open. That's our valence shell. But to add that 3d electron, I'm going back to the third energy level. Here's my 3d right there. Not a valence electron. He's back on the third energy level. He's not on the outermost energy level. So scandium has just 2 valence electrons. And that's the case for most of our D block elements. For most of these guys, open up the energy level before, so like 4s, and then go back a level to 3d. So because the S is filled up, they just have these 2 electrons as valence electrons, and these are not valence electrons. We can add more and more and more and more electrons and get that d orbital full. And for the most part, they still just have 2 valence electrons. I keep saying for the most part, watch out, there are a couple of exceptions. You remember those guys from last chapter? Chromium, molybdenum, remember they would end in D4. There is no D4. Don't use D4. So these guys take an electron from the S and get over to D5. So these guys only have 1 valence shell electron. And then same thing with copper, silver, and gold, and probably Rg down here as well. These guys end in D9. They also take an electron from the S orbital to get to D10. So watch out for those couple of exceptions from last chapter. They're only going to have 1 valence electron, but mostly these atoms have just 2 electrons. Most of D block, 2 valence electrons. And again, there's why. We're adding electrons, but we're adding it back to a non-valence shell. All right, so it brings us to Lewis dot diagrams. Guys, get good with these. We're going to be drawing them for the next 3 chapters. So this one and the 2 after it, you're going to see a lot of Lewis dot diagrams. These show only the valence electrons. These that we have up here, where we have the inner shell electrons as well, these are called Bohr diagrams. All right, hydrogen and helium, they're no different. Their only shell is the valence shell. But after that, lithium looks a whole heck of a lot like hydrogen, just one dot. We don't draw those inner two electrons. Oxygen, again, make sure you're leaving those next three open, and then finally go back and pair them up only if you have to. And I'll end here with neon. So neon is a noble gas. He's over here on P6. This is the maximum number of electrons the maximum number of valence electrons is 8. And that's something a lot of people remember. Like I always think, oh, the octet rule, atoms always want 8 electrons. And that's true, but that doesn't mean the energy level is full at 8. The second energy level is the only energy level that can only hold 8 electrons. 2s2, 2p6. You're done, you're closed off. There is no 2d. But everything else, not level 1, we'll get back to that, but everything else has D block, which has 10 more electrons. So you can actually put a total of 18 electrons on the third energy level. By the time you get to the fourth energy level, you've got 14 more in F. So you can put a total of 32 electrons on the fourth energy level. We're not done at 8. The reason why everybody thinks about 8, though, is because your valence shell is full at 8. The only sublevels that are on the same energy level are S and P. So S and P are on the correct energy level. By the time you get to D, you're a level behind. So 3D only opens after you finished the 2S. I'm sorry, the 4S. It's a level behind, not a level in front. So our fourth energy level has already been opened, and we go back to 3D. By the time we get to 4D, our fifth energy level is opened. So you can only ever have 8 valence electrons, even though you can have more total electrons. Again, you're adding them back after you've already opened up a new valence shell. All right, let's take a little closer look at the periodic table. All right, so on the periodic table, rows, and if you aren't sure which way rows go left and right, so it might be helpful to add the arrow here, left to right, or rows. These are called periods. So rows are called periods, and they show the valence energy level. Third row, third period, that means the third valence energy level. Fourth row, that's the fourth period, and that shows the fourth valence level. Your outermost energy level for atoms on this row, on this period, is 4. Now, ultimately, periods are not terribly important. Elements in the same period are not necessarily alike at all. Potassium, number 19, krypton, number 36, couldn't be more different. They're incredibly different atoms, even though they're on the same period. What's more important are the columns. And again, if you're not sure of the difference between rows and columns, watch out for that. Rows go left and right, columns go up and down. And columns are called groups or families. I usually call them groups, but you're going to hear them called families, so you got to kind of know that term as well. So elements in the same group or family behave very similarly because they have the same number of valence electrons. So columns or families, lithium and francium, way down here at the bottom, even though they're really far apart, like 3 versus 87, they behave very, very similarly. The reason why, they all have one valence electron, the S1. So they behave almost identically to one another. So elements in the same group or family behave the same, have the same properties, even if some are really, really large, some are really, really small, doesn't matter. They're going to behave the same because they have the same valence electrons. Go back a quick page here. Hopefully it kind of makes sense. It's that valence shell. If you imagine one of these atoms just kind of floating around, it's this valence shell, the outer shell, that's going to interact with its surrounding, with other atoms. This is going to be what bumps into that, and it's those outer shell electrons that are going to end up bonding or exchanging energy or whatever they end up doing. It's only that outer shell, generally that outer shell, that interacts. So it's the valence electrons that are important. All right, a couple of groups to know. Group 1 are the alkali metals. So that's this first group here. Includes lithium, sodium, potassium, rubidium, cesium, and francium. Just 2 letters. There we go. They all have just one valence electron. That's why they behave the same. And their behavior is that they're very reactive. These are highly reactive metals, the alkali metals. The reason why? Well, they all have just one electron. And if they're able to get rid of it and go back to P6, remember how this is the most stable place to be, P6, everyone would like to be there. Well, if they can get rid of that one electron, they're at P6. They just got to get rid of one extra electron and they're there. So they're very highly reactive. Trying to get rid of that electron, give it to anyone who possibly even take it. They can force it onto some people, say, hey, I got this electron, take this electron. So they're very highly reactive. They want to get rid of that electron. Here are the group 1 alkali metals. Someone you should notice is missing. Hydrogen. Hydrogen's not a metal. He does behave an awful lot like these guys. He does have one valence electron, but he's not like the rest of them. He's not a metal, so he's not an alkali metal. Onward and upward. Next up, we have group 2. These are the alkaline earth metals. So I know it's a really similar term. You got to kind of memorize the difference between them. I always remember 2, more than 1, and this is a more of a name than alkali metals. So here's our group 2 elements, the alkaline earth metals. These guys all have 2 valence electrons. and they tend to be a little bit more stable than their neighbors, the alkali metals. Those two valence electrons fill up the S2, and a full sublevel S2 is not a terrible place to be. So not as reactive as group 1. All right, next up, all of D block. These are considered transition metals. And then we group them together. Whoops, we group them together because generally they all have 2 valence electrons. And those 2 outer shell electrons are these 2 right here. So this is our D block. These are our 2 outer shell electrons. Most of them have 2 electrons. And a couple of exceptions, don't forget about that, those guys. But generally, they have 2 valence electrons. F block. So these boys down here at the bottom, we call them the inner transition metals. Again, think about it, they should fit inside of this group here. So they're the inner transitional metals, and I have no notes. The only thing you need to know about them is that they're called the inner transition metals. No more notes to add about those guys. We will not work with them very much. All right, so skipping ahead. So skipping ahead to group 15. So that's over here. It's everyone under nitrogen. These are called the pnictogens. So pnictogen almost looks like nitrogen. Maybe that helps. But these are the pnictogens. We skipped over group 13 and group 14. Collectively, I don't know if they have a name. You just refer to these guys as the boron family. These guys as the carbon family. So anybody under carbon is in carbon's family. Anybody under boron is the boron family. Generally, the pnictogens are more stable than their neighbors. Any guesses why? The pnictogens have a half full sublevel. An up arrow on each orbital, that's a half full sublevel. That's not a terrible place to be. It's not the most stable thing in the world, but it's more stable than having just 2 up arrows and not having this third one, like carbon. And it's more stable than having 4 arrows, 3 up and 1 down right here, like oxygen. So this is better than its neighbors. So generally, more stable than its neighbors. Group 16 are called the chalcogens. That's this group here under oxygen. Again, I don't really have any other notes to add for these guys. To be honest with you, just got to kind of know the name. Group 17 are the halogens. So that's fluorine, chlorine, bromine, and iodine. These guys have 7 valence electrons. They're almost there. They're almost to a full octet, a full 8. So just like their counterparts on their side of the periodic table, they are highly reactive. They'll do just about anything to get that 1 electron. They'll take it, they want it, they're highly reactive. And then finally, probably the most well-known of the groups. Group 18 here, the noble gases, they have a full valence shell, and that makes them virtually non-reactive. The word for that is inert. They don't react, they don't do anything. In fact, we didn't even discover them until about 100 years ago, a little over 100 years ago, which, I mean, if you think about it, in the grand scheme of things, that's not that long ago. A lot of elements were discovered thousands of years ago. That's why they have names or nicknames that don't really make a whole lot of sense. Like iron, why in the world would iron be Fe? Doesn't make a whole lot of sense to us. Shouldn't it be Ir? And there is an element Ir. It's iridium. But iron has a Latin name, Latin as in the Romans who ruled the world 2,000 years ago. And their name for iron is ferrous. Same with silver and gold. And these nicknames for silver make no sense unless you know the Latin argentium for silver, or the Latin Aurelius, beryllium for gold. So a lot of elements are really, really old. The noble gases are, again, within the last 150 years, less than that, pretty new. And the reason is because they're non-reactive. They just don't react. They are completely satisfied with who they are, and they have their 8 valence electrons. So they're good. They're set, with the exception of helium, who is a noble gas. You guys remember we started today? I told you hydrogen is not a metal, so it doesn't fit in. It does behave like the alkali metals, but it's not a metal. Helium is a noble gas. He's only got 2 electrons, but his outer shell is full because that first energy level is full at only 2 electrons. All right, one more thing to add. You should hopefully see this on your periodic table. I'll point it out to you since I have a periodic table right here. See that bold stair step line? That's a very important line. So aluminum is right here, boron is right here. This differentiates nonmetals on the right from metals on the left. So knowing your nonmetals versus your metals is very important. Things that touch the stair step line are called metalloids. And metalloids are really cool and important because they have properties that make them both or either metals and nonmetals. For instance, silicone, it's a metalloid, really, really important in the computing industry. You've heard of Silicon Valley. Silicone, the reason why it's so important is that we can turn it on and off. We can turn it on to a metal and it can have the properties of metal, and then we can turn it off and have the properties of non-metal, specifically the ability to conduct electricity or the ability to not conduct electricity, or lack of the ability to conduct electricity. That's what makes silicone so important. There is one exception to touching the stair step line, and that is aluminum. Aluminum is a metal, not a metalloid. It does not have non-metal properties. He is a full-on metal. All right, so there's some information for you about the periodic table. As usual, that first section, quite a bit of notes, but hopefully it'll be all downhill from here. So I'll see you next time. Talk about some of the trends we're going to see on the periodic table.